Hello, hello. We're going to now kind of get the last of the derivative rules that we're going to really be adding to our tool belt. The derivatives of inverse trigonometric functions. So first, I want to remind you what inverse trigonometric functions are, and we'll go from there. So first, the inverse sine function, and it's sometimes called the arcsine function. It's when we're saying that it's written like this: sine with a -1 exponent, but it's not an exponent. That means inverse sine. The sine inverse of x equals y is equivalent to the sine of y equals x. But this is only for values of y between pi over 2 and -pi over 2. So, for example, the sine inverse of 1/2 is the angle, right, that gives you a sine of this whose sine is 1/2. So if you think about the unit circle, right, to have the sine be at 1/2, you might remember that is an angle of pi over 6, or 30 degrees. Another example, the tangent of the arcsine of 1/3. Nice thing is you don't actually need to know what angle it is, because you can actually work from the idea of the unit circle, right? So if the arcsine of 1/3, you have to think what angle is going to have 1/3 as its height. Well, it doesn't really matter if you know this is 1/3 and that's 1, you can find the length of the other side, because 1 squared equals 1/3 squared plus, we'll call it x squared, right? So this is 9/9 plus 1/9. Oops, sorry. 9/9 equals 1/9 plus x squared. So x squared is 8/9, which is to say that x is square root 8. That's 2√2 over 3. Okay, so if that's the value of x, what's the tangent of such a triangle? The tangent is going to be 1/3 divided by 2√2 over 3, which, doing the division of fractions as multiplying by the reciprocal, it would look like this. It's going to be 1 over 2√2, because those 3's cancel. So, like I said, we don't actually need to find out what exactly the angle is, because once we know the dimensions of this triangle in a unit circle, then we can find the tangent of it. Okay, so now we get to the theorem which tells us what is the derivative of the arcsine, or the inverse sine of x. It's 1 over square root of 1 minus x squared. And this might seem completely wacky and out of the blue, but in fact, it's not that crazy, because if you can find this if you write x equals the sine of y, and we take an implicit derivative of this thing, right? So I'm going to take the derivative, I'm going to say, well, then 1 equals the cosine of y times y prime, right? And that means that y prime is 1 over the cosine of y, but I want to write cosine y in terms of x. Remember the relationship that sine squared of y plus the cosine squared of y equals 1. So the cosine squared of y equals 1 minus the sine squared of y, right? Well, what's the sine squared of y? That's x, because the sine of y is x, so that's 1 minus x squared. That means the cosine of y is the square root of 1 minus x squared. So this is 1 over square root of 1 minus x squared. That's what this comes from. This comes from an implicit differentiation and using this Pythagorean identity. This allows us to write, get this, and so actually we'll do the same thing shortly to get the derivative of the cosine inverse. But first, let's just let's just do a quick example of this. Okay, so let's say f of x Okay, so f of x is the sine inverse of x squared minus 1. First, it's worth understanding what is the domain of such a function. Remember, for the sine, you don't have to worry about the input of the sine being anything. The sine function takes all inputs, but the sine inverse is only the sine inverse domain is just from -1 to 1. And so that means that x squared minus 1 has to be between -1 and 1. If I add 1 to all of those, that means 0 less than or equal to x squared less than or equal to 2. So that means that x is going to be, if x squared, let's see, x is, when x is squared, it's always going to be positive. So that means x can be anywhere between the square root of 2 and negative square root of 2. And that'll be okay. However, so this is the domain of that's the domain of f, right? However, for the derivative, well, you'll see. Let's find the derivative. The derivative is not going to be defined basically on the endpoints of this domain. The derivative is going to be, like I said, it's 1 over the square root of 1 minus this thing squared. And the thing, that's the thing. So it's x squared minus 1 squared times, because it's the chain rule always applies, times the derivative of x squared minus 1, which is going to be a 2x. Let's just, I'm going to expand out that denominator. So that's going to be, let's see, 2x over square root of 1 minus, I'll keep it in parentheses, x squared minus 1, that's going to be x to the 4th, minus 2x squared plus 1, right? And so I'm going to have, that's going to be 2x over square root of 1 minus, that's going to be minus a minus. I'll put the 2x squared first, minus, not 4, minus x to the 4th. The 1 minus 1, those are gone. And actually, I can take the x squared out. Let's write this as 2x over x times 2 minus x squared. X's can cancel. So we can simplify this even further. 2 over square root of 2 minus x squared. Okay, the domain of this, the domain of f prime, well, because we have square root of 2 minus x squared in the denominator, we need 2 minus x squared to be not, it has to be less than, well, I guess it could be, and it is just as long as it's as long as it's greater than 0, we're okay. This is equivalent to writing x squared less than 2. That means x is not between, it's between square root 2 and square root of negative 2. So the derivative is only defined on the interior of the domain of f. But that makes sense, right? It's not going to be differentiable on the endpoints because you couldn't think of limits coming from both directions. Excuse me. So the inverse cosine function, if we say that the cosine inverse of x is y, that's just another way of saying the cosine of y is x, right? It's the same idea. And this is going to be true for any y between 0 and pi. Now that these are defined, I think it's worth just mentioning a few facts about kind of cosines and the function and the inverse function, kind of how they wrap around each other. Okay, so if you're taking the sine inverse of the sine of x, it's like saying, what is the angle whose sine is x? No. What's the angle of the sine of x? If x is the angle, and you take its sine, and you ask, well, what angle gave you that sine? Well, it was x. But this is only going to be the case for x between negative pi over 2 and pi over 2. That's because that's the domain of the sine inverse. For the sine of the sine inverse of x, you could, of course, it's going to be x, but it's only going to be valid for values of x between -1 and 1, because that's the domain of the sine function. Sorry, that's the that's the range of the sine function. I think I said it all backwards. Okay, for the sine inverse of the sine of x, because the sine inverse is only going to give you values of x between negative pi over 2 and pi over 2, this the function inverse of the function is only going to give you equal to the identity x for those angles that are in that range. For the sine of the sine inverse of x, that will equal x, but only for values of x between -1 and 1, because the sine function will only give you a value between -1 and 1, right? That's the range of the sine, and so you couldn't throw any number in the world in for x and expect to get x as a result, because the domain of the sine inverse is just -1 to 1. Similar for the cosine of inverse of the cosine, but because of the way cosine inverse is set up, you can only throw in values of x that are between 0 and pi inclusive, because the cosine inverse, that's the range of the cosine inverse function, and so it's only going to be equal to x if x was between those values to begin with. All right, so I think that's enough of that. Okay, so the derivative of the cosine inverse of x is the negative of 1 over square root 1 minus x squared. And once again, we can find this if we were to write the cosine of, if we were to write cosine y equals x and do the implicit, saying y equals cos inverse of x, right? That means that cosine of y is equal to x. Then the derivative with implicit differentiation, we're going to have negative sine of y times y prime equals 1. Y prime is 1 over, it's -1 over sine y, and by the Pythagorean theorem, the sine of y is equal to the square root of 1 minus the cosine squared of y, and that's 1 minus x squared, because that's what the cosine of y is, it's x, right? So this is -1 over square root 1 minus x squared, that negative sign out front. And that's how you can prove or derive the derivative of the cosine inverse function. All right, the inverse tangent function, when we say the tangent inverse of x equals y, that's equivalent to saying, of course, the tangent of y equals x. Notice, though, that the tangent inverse is only going to give you a value of y between, but not inclusive of negative pi over 2 and pi over 2, right? Because the tangent isn't defined for pi over 2 or negative pi over 2. That's not defined because those are asymptotes on the tangent function. Okay, so the cosine of, I want to look at how you might simplify these a little bit. The cosine of the tangent inverse of x. Well, one thing that we can do, if we want to write the tangent inverse of x, the angle whose tangent is x can be found by taking a triangle who's got, remember the tangent is the opposite over the adjacent, right? So if it's x over 1 would be x. And then from this you can see that the hypotenuse is going to be the square root of 1 plus x squared. With that in mind, then, the cosine of theta, which is, this is the angle, which I'm not actually going to solve for, but the cosine of theta would just be the adjacent over the hypotenuse, right? It's going to be 1 over the square root of 1 plus x squared. Okay, so let's think about this. What would be the limit of the arctan of 1 over x minus 2? It might be easier to let t be x minus 2, and we can see that let's t minus 2 is going to be x. As if x is going to 2 from the right, that means that that t minus 2 is going to 2 from the right. Okay, that means t is going to 0 from the right. It might be a little bit easier to think about. Now, what happens when the arctan is going to 1 over, let's see. All right, let's take a look at this limit. The limit of the arctangent of 1 over x minus 2 as x goes to 2 from the right. Now, I think that for me, I would like to kind of using a transformation where we let, say, t be x minus 2. It's a little easier to think of this as x is going to 2. That means t is going to go to 0. This is the limit as t is approaching 0 from the right of the arctan 1 over 1 over t. Okay. So we can also think of this as if we I mean just kind of taking it one step at a time. If we let 1 over t be some other thing, call it, I don't know, u. Okay. As t is approaching 0 from the right, that means u is going to infinity, positive infinity. So this is the limit as u goes to infinity of the arc tangent of u. Okay, what's the limit of the arctangent? It's probably helpful to just think about what the arctangent looks like. The tangent function looks like this. If we were to reflect this over the diagonal, then you can see that the arctangent, this is y equals arctangent of x. And the asymptote here is the same as the asymptote of the tangent. This is at pi over 2, at pi over 2. So the arctangent approaches pi over 2 as the thing inside it gets bigger and bigger and bigger and bigger. Okay, so the derivative of the tangent of the arctangent of the tangent inverse of x, it's 1 over square root of 1 plus x squared. And again, you can kind of argue, you can find this by saying, well, if we let y be the tangent inverse of x, that's the same as saying that x equals the tangent of y. Take the derivative of both sides implicitly, right? We're going to get 1 equals the secant squared of y times y prime. Okay. So the derivative of the inverse tangent now of x is 1 over 1 plus x squared. You can see that by if we set up like y equals the inverse tangent of x, this is the same as saying x equals the tangent of y. If you take the derivative implicitly, you're going to get 1 equals secant squared of y times y prime. Divide both sides by secant squared. Remember that secant of y is just 1 over the cosine of y, right? So I'm going to actually get cosine squared of y equals y prime. However, we should put this into perspective. If x was the tangent of y, let's put this. Let's write this. If this is the angle y, okay, and x is the tangent, that means x would be the opposite side. 1 is the adjacent side. That means the hypotenuse is 1 plus x squared. So the cosine of y, that's opposite over hypotenuse. It's 1 over square root 1 plus x squared, right? So cosine squared of y, that's 1 over 1 plus x squared. And that's our derivative. Okay, so let's see. Okay, so take f of x as tangent inverse of square root x. What is going to be the derivative of f? Well, we just said it was going to be the derivative of our inverse tangent is 1 over 1 plus the thing squared, whatever that thing happened to be, and that thing is the square root of x. So it's the square root of x squared, but we're not done. Chain rule, always chain rule, always chain rule. The derivative of square root of x is 1 over 2 root x. That is what we need. Now we can clean this up a little bit, right? This is going to be, let's see, 1 over, that's 1 plus x, but that's going to be times 2 root x. So I guess we could write this as 1 over 2 root x plus 2x root x if you fancy it. So there you go. We got the derivatives of the inverse cosine, inverse sine, and inverse tangent. There's actually derivatives for the inverse secant, the inverse cosecant, and the inverse cotangent, which you can get by you can look those up in a table if you ever need them. They're available. And so, yeah, so now we just got to get some practice using these. All right. Bye-bye.